Today we are about to see another very practical application, the elliptic curve digital signature algorithm. Once again we meet our two friends, Alice and Bob. Hi Alice.
Hi.
Hi Bob.
Hi.
These guys can already exchange encryption keys, so now they want to ensure the integrity and authenticity of their communication. This requires them to use some digital signature scheme. As we already know, they agreed to use the elliptic curve designed throughout this series and the point 45 as their generator. We also know that Alice has a private key represented by her secret number 3 and that she sent Bob the corresponding public point 1322. So now it's time for her to sign the message she wants to send to Bob. To do it, she first calculates some digest value Z that represents the message she is willing to sign. Such value must be of the same bit size as the order of the curve used. As the order of the curve is 23, it means 5-bit value is required.
The digest value Z is 10.
Now Alice rolls dice to choose a random number k between 1 and the order of the curve.
I rolled 19.
Now she multiplies the generator by this number k to get the point k.
Using the double and add algorithm, I calculate the point k as a 19 multiply of the generator. The resulting point k has coordinates 9, 17.
The x-coordinate of the point k is the first half of our signature, usually labeled r. It serves as a reference value used for verifying the signature. Now Alice calculates the other half of the signature by using modular arithmetics with the order of the curve as the modulus.
First, I calculate the multiplicative inverse of k modulo the order of the curve. The multiplicative inverse of 19 modulo 23 is 17. That's because 17 times 19 modulo 23 is 1. Now I sum the digest value Z with the product of R and my private number A, everything modulo 23. 10 plus 9 times 3 modulo 23 is 14. The product of the multiplicative inverse of k and this value is S, the second half of the signature. 17 times 14 modulo 23 is 8. The signature of the message with digest value Z equal to 10 is therefore the pair of numbers 9, 8.
When sending the message with digest value Z equal to 10, Alice attaches the signature pair 9, 8 to it. Bob receives the signature, and before starting the verification, he calculates the message digest Z and comes to the same value as Alice used.
The message digest value Z is 10.
The next step he has to perform is calculating the value W from the signature number S. The value W equals to the multiplicative inverse of number S modulo the order of the curve.
The number W is 3 because 3 times 8 modulo 23 is 1.
Now he calculates two multipliers, U1 and U2. The former is the product of the digest value Z and the number W modulo the order of the curve, and the latter is the product of the first half of the signature R and the number W, once again modulo the order of the curve.
Multiplying 10 times 3 modulo 23 gives me the value 7, which is the coefficient U1. And multiplying 9 times 3 modulo 23 gives me 4, which is the coefficient U2.
To finally verify the signature, Bob multiplies the generator by the coefficient U1, then he multiplies Alice's public point A by the coefficient U2, and summing these 2 points give him a signature verification point labeled S.
By using the double and add algorithm, I compute 7 times G, which gives me the point 17, 8. Then, using the same algorithm, I compute the point 4 times A, which is 10, 12. Summing these 2 points, I end up with the point S, with coordinates 9, 17.
Although it was a bit longer than you might have expected, it is finally possible to verify the signature.
The value R is 9, and the x-coordinate of the point S is 9 as well. Therefore, the signature is valid.
This was our most complex elliptic curve algorithm so far. Thank you for staying with us for so long. And again, thank you Alice and thank you Bob.
You're welcome.
No problem.
Thank you for watching. And remember to subscribe to our YouTube channel and to follow us on Twitter. There is more to come.